The question reads, a 2 nanocoulomb charge is at the origin, and a minus 4 nanocoulomb charge is at x equals 1 centimeter. At what x coordinate would you place a proton so that it would experience no net force? Well, let's look at that. So since we have two charges along a straight line, they're along an x-axis. Let's go ahead and begin by drawing our x-axis. And we'll go ahead and put the units of this x-axis in centimeters. I will put the origin, I guess I'll just, for now, put the origin right here where the y-axis is vertical. And they tell us that we have a 2 nanocoulomb charge placed right at the origin. I am going to illustrate that charge. Maybe that 2 nanocoulomb charge will be in red. So let me illustrate that. Here is our charge. I'll go ahead and label this charge Q1. And I will define Q1 to be equal to 2 nanocoulombs. Now remember, a nano is a 10 to the minus 9. So that's 2 times 10 to the minus 9 coulombs. Then they tell us that we have a charge situated at 1 centimeter. I will make my 1 centimeter mark here. We'll just call this 1.0. And this charge is a negative charge. I will call this negative charge Q2. And let's go ahead and define, and in fact, I'm going to call this negative charge minus Q2. Now, the reason why is it's for consistency. Signs can get tricky, especially dealing with vectors and especially dealing with scalars mixed with vectors. Signs can be confusing. So a convention that I follow is every time I write a variable that represents a vector, it will always represent a magnitude. Now, I will also, almost every time I represent just a variable, I like that variable to represent a magnitude. And this allows me to avoid some problems later, but it does kind of require that I look at sketches and I look at the direction of force vectors and whatnot so I can get the appropriate sign. So what that means is since I put a minus in front of Q2, Q2 is then going to be 4 nanocoulombs. So this is, now I'm going to keep track of that minus sign. Now, whenever you see relationships between variables where one variable can be expressed as a multiple of another variable, my recommendation to you is to express one as a multiple of the other. You don't have to, but you will see throughout the course of this semester that oftentimes when you can express one variable as a multiple of another variable, that the algebra becomes oftentimes a lot simpler. So what I see here is since Q2 has twice the charge as Q1 in magnitude, I'm just illustrating that by saying Q2 is equal to 2Q1. All right, so the question for this problem is, where do we need to place a proton so that it would experience no net force? Well, let's first write down what we know about protons. The magnitude of the charge of a proton is the same as the magnitude of the charge of an electron. So we can represent the charge of a proton as just E. And E, we have defined it to be 1.602 times 10 to the minus 19th coulombs. So what we're doing here is we're just spending some time setting up our problem. My recommendation is you should be spending about 75% of your time just setting up the problems, writing down the information, sketching your picture, defining your variables. That 75%, when you get to the last 25% where you're actually doing the algebra, you'll see that if you've set things up pretty well and methodically, the algebraic work goes a little bit easier. Okay, so let's look at what we're trying to find. We have a proton. For now, I'll just go ahead and draw the proton rather. And let me just use a circle. I'm going to draw the proton right here for now. There is our proton. The question is, where do we need to position that proton for it to be zero net charge on it? Or a zero net force on it, rather. Well, let's see. Okay, so I saw a chat. Okay, so Stephen says to the left of charge 1. So thanks, Stephen. Well, let's explore that. Let's explore the different regions. And I think Stephen's going to be right, but I'm not quite sure yet. So if we divide this graph into 3 regions, basically the regions separated based off of where the charges are. So I'll do a region to the left of charge 1. Let's call this region 1. Let's do a region in between charges 1 and 2. We'll call this region 2. And then I'll do a region to the right of charge 2. I'll call this region 3. The reason why I'm thinking of dividing this into regions, it's because that since there's electrical forces acting on our charge, where that charge is going to dictate how the forces are acting on that charge. Are the forces pulling the charges to the left? Are they pulling the charges to the right? We don't know. So what I'm going to do is I'm going to take this proton and let's sketch qualitatively how the electric forces will act on the proton in the 3 different regions. So if we look at the proton, let's say in region 1, that's the region that Stephen suggested. In region 1, let's look at the effect charge 1 has on our proton. Our proton is a positive charge. Charge 1 is a positive charge. 2 positive charges will repel each other. So in region 1, the proton will experience a repulsive force from the positive charge. So I'll illustrate that with just a vector arrow to the right. Now let's look at charge 2. Will charge 2 repel or attract the proton? And I wrote Q1 there, that I should have wrote Q sub P for the proton. And the proton suddenly turned red. Let me turn it back blue. So for the proton, and let me do this. Okay, so for the proton, will charge 2 attract the proton or repel the proton? If you're not sure, look at the sign on charge 2. And I'm going to just double check the chat, make sure I don't have anything. Okay, so Carissa says that charge 2 will attract the proton. And that's correct, because since charge 2 is opposite in sign to charge 1, charge 2 will attract the proton. Let's illustrate that. So when we illustrate that, I will just do my attractive vector. It's going to be shorter than the force vector I drew for charge 1. I will just call this the electric force on the proton from charge 2. Excuse me. And I'll call this on the left the electric force on the proton from charge 1. Okay, charge 1 is repelling the proton to the left. Charge 2 is attracting the proton to the right. Okay, so definitely it seems like it would be possible that there is a position to the left of charge 1 where our proton would have no net force, because in order for it to have a net force, whatever force is going in one direction must be balanced by a force going in the opposite direction, at least one force going in the opposite direction. So that's a possibility. I'm going to look at the other two regions too. I'm going to look at region 2. And in region 2, I see that the negative charge will still attract the proton. So I will call this the force on the electric force on the proton from charge 2. And charge 1 will still repel the proton, and charge 1 having half the magnitude of charge as charge 2, maybe I'll draw this vector a little smaller, but notice the electric force on the proton from charge 1 is also pointing in the positive x direction. It is impossible for the proton to be in equilibrium in region 2, because we need at least one of those forces to be in the direction opposite the other force. So we can rule out region 2 as being a possibility. Now let's look at region 3. So in region 3, if our proton were in region 3, the charge Q2 is still attractive. So this will be the electric force on the proton from charge 2, and charge 1 will still be repulsive. Now here's the thing. Conceptually, I know that region 3, it should be impossible as well for the proton to be in equilibrium. Conceptually, I should know that. The reason why I know that conceptually is charge 2 has a magnitude greater than charge 1. I also know that the distance between the proton and charge 2 is less than the distance between the proton and charge 1. What this means is if you were to look at the electric force on the proton from charge 2, it's going to be greater than the electric force on the proton from charge 1. And the reason why is if you look at Coulomb's law for these point charges is the charge of the proton, charge 2, over the distance between the proton and charge 2 squared. Because, again, the numerator of the left side is greater than the numerator on the right side, which involves charge 1. And because the denominator on the left side is greater than the denominator on the right side, the denominator on the left side is smaller than the denominator on the right side, I know that the electric force due to charge 2 must be greater than the electric force due to charge 1. For those reasons, I could rule out region 3. However, if you're not convinced, we could rule it out algebraically. I'll let you rule that out algebraically, but for us, I feel like Stephen's suggestion of region 1 is the right region to begin with. So let's begin there with the actual solution of our problem. Any questions so far? Okay, so I'm going to just go ahead and go to our next page. I'm going to quickly resketch our picture, and then we are going to focus on region 1. So we have an x-axis in centimeters. We have the y-axis up here. Here's charge 1. Here's charge 2. Charge 2 is a distance, is at the location x equals 1 centimeter. I'll just go ahead and call this A because I like dealing with variables. It's easier for me to write A than 1.0 centimeters every time. And we are going to focus our attention on region 1, where we believe the proton must be located. So in region 1, the proton must be at a position which I will call the position in region 1. I will just call it B. So B is going to, and maybe I will call it negative B. So B is just some value on the negative x-axis. So in essence, we're finding the value for B. Now, at this point, we have the repulsive, let's do that again. We have the repulsive electric force on the proton from charge 1 and the attractive electric force on the proton from charge 2. And that position would be the position in which those two forces balance, giving us a zero net force. We could write the sum of the forces in the x direction on the proton is equal to the electric force or the Coulomb force on the proton from charge 2 minus the Coulomb force on the proton from charge 1. The reason why it's a minus is from my sketch. I'm using my sketch to tell me the signs that I need for my forces. So it's a minus because the force on the proton from charge 1 is pointing in the negative x direction. This is equal to the product of the mass of the proton times the proton's acceleration in the x direction. Since our proton has zero net force, there is zero acceleration. Because there is zero acceleration, these two forces must balance. We know that the Coulomb force on the proton from charge 2 must be equal to the Coulomb force on the proton from charge 1. Let's write Coulomb's force for each pair of particles, the Coulomb force on the proton from charge 2 over the distance, and I'll just call this distance P2, the distance between the proton and charge 2 squared. Let's look at that in our picture. In our picture, that is this distance squared. So if we look at that distance is going to be the 1 centimeter, which I am calling A, plus B, where again, when I write a variable, the variable represents a magnitude. So the distance between the proton and charge 2 is the distance A plus B, and we are trying to find B because that is where on the x-axis charge the proton will be. So we now have an expression for the distance between the proton and charge 2, and we know that that has to be equal to the Coulomb's constant times the charge of the proton times the charge of charge 1 divided by the distance between the proton and charge 1 squared. Now notice all of these variables are magnitudes. I don't have to then plug in a minus sign for charge 2, which I should still indicate that in my picture with the minus sign in front of Q2 in my picture. But once I sketch the vectors and use the vector arrows to figure out direction and use that to write my Newton's second law equation, I'm dealing with magnitudes. Now, the distance between the proton and charge 1, well, that's the same distance as B. So I will write the distance between the proton and charge 1 is equal to B. All right, well, let's simplify our results. On the left side, we have the Coulomb constant. On the right side, we have the Coulomb constant. No need to plug in those values. They cancel out. On the left side, we have the charge of the proton. On the right side, we have a charge of the proton. Those values cancel out. We earlier said that the magnitude of Q2 is equal to twice the magnitude of Q1. So on the left side, Q2 is equal to 2Q1 over A plus B quantity squared as the distance between the proton and charge 2. And on the right side, we have Q1 over B squared. Oh, notice, Q1's on both sides. Guess what? We don't have to plug those in. This is one reason why I like to solve things in terms of variables, because when you finally do the algebra, you oftentimes have a much simpler expression. Oops. So this is the equation we have so far. Remember, our goal is to solve for B. So I'm going to have to isolate B from this equation. Since I have a single fraction on each side of the equality, I'm going to just flip it. So we have an A plus B quantity squared over 2 on the left, and then we have a B squared on the right. Now what I'm going to do is I'm going to go ahead and multiply out the A plus B. That is going to be, or actually rather, I guess we could just take the square root of B on either side, but nah, I don't want to do that because we could forget a minus sign here or there. But I really want to. So yeah, maybe I will. Well, I'll just do my first thinking, and then maybe I'll go back and see my second thinking and see if the answers are consistent. But for now, I'm probably going to do this with more work than I really need to. Part of the reason why is I just want to show you, I just want to remind you of quadratic equations and quadratic functions, even though I don't think, I'm pretty confident I don't need a quadratic equation on this one. And we'll go back and do it without, but I'm going to use this as an opportunity. Now, gosh, but it's so easy. Why do all of that work? Okay, let's do the easy one first. The easy one first, or rather, I meant let's do the quadratic one first, and then we'll go back and do it the easy way. So if we multiplied the left side, and maybe I'll just separate my page, the left side will be for the quadratic. We have a squared plus 2ab plus b squared on the left, and that is equal to 2b squared on the right. This is now 2b squared minus b squared minus 2ab minus a squared is equal to 0. You might be noticing that I'm putting this in the form of a quadratic equation. So this now becomes b squared minus 2ab minus a squared is equal to 0. This can be solved. This equation is a quadratic equation, and you might be saying, well, Mel, how can it be a quadratic equation when I just have a's and b's? Well, remember, b is our unknown. And remember, B just corresponds to a position along the x-axis. So if it's easier to look at, we could write x squared minus 2ax minus a squared is equal to 0. And that would represent the same thing where we are saying let x equals to b. Now that we see that that is clearly a quadratic equation, let's go ahead and use the quadratic formula, which says x is equal to minus the coefficient of the second term, so that's minus a minus 2a, plus or minus the square root of that second term squared, so that's minus 2a squared, minus 4 times the first term times the last term, all over 2 times the first term. Well, this becomes 2a plus or minus 4a squared plus 4a squared over 2. Now, notice underneath the square root, we could factor out a 4. And the square root of 4 is 2. Guess what? We have a 2 in the numerator, 2 in the denominator. Those all cancel out. Now we have x equals a plus or minus, and inside we are left with a 2a squared. So this is a plus or minus a root 2, if I didn't make any mistakes. So I'm going to pause right now to double check my work, and you all are here to double check my work as well. I'll just scroll up. And if you have any questions, go ahead and fire them off. And I will do this, what I think is an alternative way to see if it works out. Alternative from the algebra point of view. Is everyone okay with what we have up to this step? Okay, cool. Okay, so I went the quadratic equation route. We'll do it the other route, which will be a lot simpler, is what I'm guessing. So I'm just reviewing my work. I always like to review my work when I can. So I squared the left side, a squared plus 2ab plus b squared, 2b squared on the right side. I moved everything over. I have a b squared minus 2ab minus a squared. Use the quadratic formula, and I think this looks good so far. What do you all think? Do you think that and let me do the chat again, do you think that is okay for now? Okay, cool. So we're good. So then notice how this says there are two possibilities for a solution. One possibility for a solution is at a minus, oops, forgive me on that. One possibility for, all my notifications are coming in at this point. Problem with working on a single screen. One possibility of solution is we are going to be along the, well, let's see. Okay, so this is the value x, and this should all be in terms of a magnitude because we solved this as a magnitude, and x was equal to b. So that means there are two possibilities. One possibility is a plus value. One possibility is a minus value. Okay, well, let's interpret the possibilities then. So remember, A is 1 centimeter. So this is 1.0 centimeters. And I don't have my calculator on me, but can someone tell me, and I think this is to two significant figures. Let's see, yes, to two significant figures. Can someone tell me the to two sig figs, what you get for these? And I guess I could pull out the calculator that's actually on the computer, if unless you guys are about to. Okay, 2.4 centimeters and 0.41 centimeters. Thank you. So 2.40 centimeters and what was it? Negative 0.41 centimeters. Okay, two possibilities. Is it possible? So let's look at the 2.4 centimeters. And we'll look at it on both sides. 2.4 centimeters would be a point, if we were to look at that as a positive x value, that would be a point probably around here as a positive x, and it would be a point probably around here on the negative x. What do you think? And then we have the minus 4.1 centimeters. What do you guys think? And feel free to do it in the chat or audibly. Can it be both? Is it possible that it really is both? Why or why not? Okay, so one person's saying it should be positive because we are saying it is at minus b. Okay, so in other words, Stephen, you're saying since our values are, since I specified b being a magnitude, that it should be at the minus b. I think that's what you're saying. Okay. Anyone else? So think about it. And then, so I want to, if we could at least get one or two more thoughts, and don't worry about being wrong. Part of this is learning how to think, and we are sharing with each other in learning how to think. It's negative x direction since it's value of b, but you defined the point as a minus b. Okay. Let's see, it's negative x direction since it's value. So are you saying, I guess I'm not really clear about what you're saying. Are you saying that it should be x equals minus 2.4 centimeters? Ah, okay, I get that. Okay, good, thank you for the clarification. So it seems like Stephen and Sophie are converging on the answer that the actual result we should use is the 2.4 centimeters. And remember, when we solved this out, in solving it out, we made an assumption. Our assumption is we are in region 1. And with that, and with our assumption being in region 1, and with the idea that we're defining B to be a positive magnitude. Remember this up here? Since we define B to be a positive magnitude, that means any answer that we get that is positive is going to be in region 1. And any answer that we get is negative is going to be actually opposite the direction of where we put position B. We've already ruled out, even though the math gives us 2 solutions, we've already ruled out those 2 solutions there. And that's minus 0.41 centimeters is just basically opposite the direction of B. That minus 0.41 centimeters puts us in quadrant 2, which we ruled out. Now, the algebra doesn't really know we have constraints. The algebra doesn't know that we have physical constraints because one charge is positive and two charges are positive and one is negative. So we always have to do a reality check. Does our answer make sense with the constraints we have? And that's one reason why we spent a lot of time in just setting up the problem so we could understand what we had to deal with here. So in short, our answer is B, and this is a magnitude B. So when the question says, where is it on the x-axis? We would say x is equal to minus B, which is minus 2.40 centimeters. Okay. So I am almost out of time, but because I want to finish this problem, I'll go over a couple of minutes, and then I have to run to my first dental appointment since COVID started. So I just have to get my teeth cleaned. Not sure how I feel about that. Oh, cool. I missed what Joseph said. It's on the left because if you put it in on the right side of the diagram, then it would be closer to the larger. Beautiful, Joseph. Good. And I like how you are, I like how you're using the concepts to try and anticipate where it is and the system is in balance. So notice how Joseph is doing a reality check as well. Okay. So let's see algebraically. Again, a big reason why I wanted to do it this way is 1, I felt comfortable using the quadratic formula, but 2, the quadratic formula comes up a lot. But really, we could have solved this probably a bit more simply, and I will just go ahead and copy this to a new page. So I'll copy that, and we will put it right here. All right. And let's actually move that up a little bit. Okay, so the first thing I should have considered doing maybe was just to take the square root of both sides. So I'll take the square root of the left side, I'll take the square root of the right side. But when you take the square root, you got to remember one of those sides has to have a plus and a minus. So don't forget that. When we do that, we have A plus B equals plus or minus B root 2. And then when we isolate B, let's see if we have B minus plus B root 2 equals A. Did I copy that right side down right? Yes, okay. Root A, and then we will factor out the B1 minus plus root 2 equals A. And I'm feeling a little uncomfortable with this because this is looking a little different than what we had before, but I get A minus plus root 2. Now I could ask you to evaluate that for me, but let me just go ahead and rationalize this. So when I rationalize, I'll multiply numerator and denominator by, and then you can put it in your calculator while I'm rationalizing, because maybe I'll make a mistake rationalizing since I'm kind of rushing right now. Whenever I rush, I tend to make mistakes. So double check me. So in the numerator, we have 1. And again, you could just take this over here and put it in your calculator. I just don't have my calculator on hand right now. So the numerator, we have 1 plus or minus root 2. And in the denominator, we have, that's going to be 1 squared. And let's see, root 2, some or different. So that's going to be, give me just a moment. I'm having a momentary brain freeze. Oh, that should be minus 2. And let me just check myself by just doing one of these so I'm not doing it all in my head. And that way I could make sure I didn't make a mistake. I was just trying to save time. But often when I try and save time, I end up making a mistake, and that costs more time. So let me go ahead and do this. That's minus 1 that way. And then, so yeah, so I did do it right. And you know what? That actually is the same thing we got before. This result was identical to this right here. So yeah, just taking the square root of both sides would have been so much quicker and easier mathematically. But you'll get to know me on this. A lot of times I'll work a certain problem and I'll do it a certain way. And you might be like, wow, why is he doing it that way? Do we have to do it that way? First off, I'll say, no, you never have to do a problem the way I will work a problem. Because as long as you are doing correct mathematics and applying correct physics, there are as many ways to approach the problem as there are students in our class. Your task is to just make sure you show your work, explain your thinking. Now, why I will choose a course of action, part of this was based off of I really wanted to do the quadratic formula. Part of wanting to do the quadratic formula was familiarity. But most importantly is I know in this semester, there's going to be lots of situations in which you have functions that are quadratic that I want you to deal with. And this gave us the opportunity to review that. So sometimes in a lecture, I will do something a certain way because there's something from it I want to remind you of, or I want you to learn. And so just be aware, there's never one way to pet a cat. There's always multiple ways of petting a cat, which that's an expression my wife and I like to say. Okay, I'm out of time. Carissa, thank you so much for that question. It'll take, I have to do I'm getting my teeth cleaned and I have to do some errands today. It'll probably take a while before this gets posted. Also, I have, I'm writing up your next lab activity. And I have it almost already, but start looking for your next lab activity either this evening or I guess to give myself some breathing room. By tomorrow morning, at the latest, you should be seeing your next lab activity. Any questions before I have to sign off? Oh, it looks like, should the A have been negative? I see a question that Carissa asked. Sorry, it's taking me 5 minutes, Carissa, to get to that. But yeah, me rushing right up here, when I moved the B to this side and when I moved the A to the other side, you are in fact right. The A should have been negative all along. And fortunately, that doesn't really affect the quality of our answer. When we distribute that minus sign through, well, I'll just leave it as a minus plus. But yes, you are right. There should have been, it should have been a minus when we moved on the other side. But fortunately, we got lucky on that one. Any other questions before we sign off? Okay, everyone, have a wonderful, wonderful day. And